Now let's see how to solve linear differential equations of order n with constant coefficients. Okay, let's see. F of dy is equal to, we know, a naught dn plus a1 dn minus 1 plus a2 dn minus 2 and so on up to an equal to 0. So here the equation is equation involves 0. So f of dy is equal to 0. Now we have seen the results, right? We have seen how f of d eax is equal to f of a eax. Yes, similarly we have seen f of d eax v is equal to f of d plus a eax, and we have also seen f of d square sin ax is equal to f of minus a square sin ax, and we have seen f of d square cos ax is equal to f of minus a square cos ax. These are the 4 results we have seen. So we are going to use this to solve. So now what we have to solve is this f of dy equal to 0, and we can solve it by saying, okay, let y is equal to eax. Now just to keep it different, let's say this is mx and there is a coefficient for this, say c. Now here c and m are constants. So let's say this is a solution of f of dy is equal to 0. So if that is a solution, we can say f of m c e m x equal to 0. Now here f of m is a polynomial in m of degree n. Now you might wonder, from where did this suddenly fm came? F of m. You see, if we have ax, that a comes here. So similarly, since we have e to the power of mx, we are taking f from f of m. M is a root of f of m equal to 0. Then y is equal to cemx is a solution of f of dy equal to 0. F of m equal to 0, then we can say that this is y equal to this cemx is a solution. Okay, which implies for every value of m satisfying f of m equal to 0, we have a solution y is equal to cemx, solution of f of dy equal to 0. Also implies that sum of all these independent solutions involving n arbitrary constants will be the general solution of f of dy equal to 0. Yes, think over it carefully. So now, which means there are going to be three cases. Yes, one is roots of fm is equal to 0 are real and distinct. Say for example 1, 2, 3, something like that. Roots of f of m equal to 0 are repeating, right? They may repeat twice or more than twice as well. For now, let's look at repeating twice. So say for example 1 comma 2 comma 2, and the third case is roots of fm equal to 0 are complex numbers. And if you know the theory of equations, you know that these complex numbers would be in conjugate pairs. Okay, let's take these cases one by one and see how to solve these equations. Okay, so the first case is roots are real and distinct. So let the roots be m1, m2, m3 and so on up to mn. Then we know c1 e to the power of m1x, c2 e m2x, c3 e m3x and so on up to cn e mnx are all solutions. So in which case the general solution would be y is equal to c1 e m1x plus c2 e m2x plus c3 e m3x and so on up to c n e mnx, where c1, c2, c3 are arbitrary constants. Okay, so that is when the roots are real and distinct. Now let's look at when roots are repeated, and in this case let's look at the simplest case, that is repeated twice. So let m1 be a repeated root. So if we look at theory of equations, if x is equal to 1 comma 1, that means what? X equal to 1, x equal to 1, x minus 1 equal to 0, x minus 1 equal to 0, which means x minus 1 equal to 0, which means x minus 1 square equal to 0. Yes. So similarly here we know that d minus m1 square y is equal to 0. This d minus 1 came by this logic. This can be written as d minus m1 times d minus m1 y equal to 0. Now let's treat this as, let's say, v. Okay, so which means again 3 year of equations, the reverse logic of this means that d minus m1 equal to 0 or d minus m1 y equal to 0. And in this case, let's say this is v. So which means when we substitute back into this, we get d minus m1 v equal to 0. dv minus m1v is equal to 0. Now remember, d is nothing but d by dx. So dv by dx minus m1v equal to 0. Now let's move them around. dv by dx is equal to m1v, dv by v is equal to m1x. No, not x, dx. Now let's solve this. Let's integrate. So let's say integrating, we get dv by v is equal to integral of m1 dx. This we get log v is equal to m1x plus, let's say, c1, constant of integration. But usually when we have a log, we take the constant of integration also as a log. So let's say log c1. Now to get rid of log, this also should be log. So let's put log to the power of e to the power of m1x. This log and e will get cancelled and we will be left with m1x, which is what we have already. So we go reverse. So this we write it as log v is equal to log of e to the power of m1x plus log c1. Now using log rules, this addition becomes multiplication. So log m1x c1 times c1, and now we exponentiate both sides to get rid of log. So v is equal to c1 e to the power of m1x. This is a little bit tricky, so be clear before you proceed. Okay, so we go back to our equation. What did we have? We had d minus m1 y is equal to v, remember? So now we substitute this in place of v, which implies dy minus m1y is equal to c1e m1x. Now d is nothing but dy by dx. D is nothing but d by dx, and we have y. So dy by dx minus m1y is equal to c1e to the power of m1x. Now this is a very simple linear differential equation of order 1. So let's solve this. To solve this, we multiply it with the integral factor. The integral factor is e to the power of integral of minus m1 dx. Now when we integrate the exponent, what do we get? We get minus m1x. Minus, we can take it out. m1 dx is nothing but m1x. So now let's multiply both the sides by this integrating factor, dy by dx times e to the power of minus m1x minus m1y times e to the power of minus m1x is equal to c1 e to the power of m1x times e to the power of minus m1x. This is nothing but 1 by e to the power of m1. So this and this gets cancelled. Now let's look at this and this. Can we combine them? If you notice, this is, let's say, e to the power of minus m1x is as it is, and this is the differential, or dy by dx. Whereas here y is as it is, and this is the integral of this, differential of this. So which means we can write this as d by dx of e to the power of minus m1x times y. So basically look at this as a reverse of the product rule, or we have applied product rule on something to get this. So this is the product. We have applied the product rule on the product of this. So here, just very quickly, you can do the product rule to get back this. So this one as it is dy by dx plus y as it is, and the differential of this is minus m1 times e to the power of minus m1x, okay, equal to c 1. Okay, so from here to here using the product rule, and from here to here a reverse product rule. Okay, now let's solve this. So integrate both sides. So d by dx of e to the power of minus m1x times y is equal to integral of c1. This integral and differential get cancelled out. We are left with e to the power of minus m1x times y is equal to this. We can write it as c1x, and the constant of integration is going to be c2. Now we take this to the other side, e to the power of minus m1x, and this e to the power of minus m1x we can take it to the numerator. So c1x plus c2 e to the power of m1x. So what we have arrived at is the general solution for the roots which repeats. Actually, to be more precise, I should say part of the general solution for the roots which repeat. So the complete general solution would be y is equal to, let's reverse this numbering of the constants. So let me put this as c1 plus c2 x times e to the power of m1x plus c3 e to the power of m2x plus c4 e to the power of m3x, and so on till we have cn e to the power of mn minus 1x. Now this was the case when two roots were repeating. When, let's say, r times a root is repeating, in that case the general solution would be y is equal to c1 plus c2x plus c3x square c r x to the power of r minus 1 times e to the power of m1x, and then you will have the other terms. So you will have c r plus 1 e to the power of m, here you will have 2x plus, and so on till c n e to the power of m n minus r x. So this is general solution for a root repeating twice. Now let's look at the third case. What is the third case? Roots of fm equal to 0 has a pair of complex roots, has a complex pair. If we remove this, this makes a much better sentence. Okay, so in this case, how will we begin? Now let's say the roots are m1 is equal to alpha plus I beta, and the second root is, remember, theory of equation says that if you have a complex number as a root of an equation, its conjugate would also be a root. So we have this pair of conjugate complex numbers as the roots of the equation. So therefore our solution would be, based on our previous derivations, c1 e to the power of m1x, remember, so alpha plus I beta x plus C2 e to the power of alpha minus I beta x. Now let's open it up. C1 e to the power of alpha x times e to the power of I beta x plus C2 e to the power of alpha x times e to the power of minus I beta x. Okay. Now we have to remember a particular identity to take it further, and the identity says e to the power of I theta is equal to cos theta plus I sin theta. So here in our case I theta, so this is theta. So based on this, let's expand it. So C1 e to the power of alpha x, because here C1 we are not touching, we are just going to expand this part. So cos beta x plus I sin beta x plus C2 e to the power of alpha x times cos minus beta x plus I sin minus beta x. Okay, so C1 e to the power of alpha x times cos beta x plus I sin beta x plus C2e alpha x. Cos minus something is cos itself. Yes, so cos beta x. Now sin minus something is minus sin, so minus I sin beta x. Now again let's distribute. So C1 e to the power of alpha x cos beta x plus C1 e alpha x times I sin beta x plus C2 e alpha x cos beta x minus C2 e alpha x I sin beta x. So here cos beta is common. E alpha x is common. Similarly here sin beta x is common. E are common. So now let's group them based on that. So C1 plus C2 e alpha x cos beta x, right, plus C1 minus C2 I e alpha x, not I again, sin beta x. All this is, remember, y is equal to. So y is equal to. Now let's say C1 plus C2 is equal to A. Let's say C1 minus C2 I is equal to B. Now why am I taking C1 plus C2 here and C1 minus C2 I also including? Because we know we are starting with complex numbers, so we are in the domain of the complex numbers. So in a complex number we need to have a real part and an imaginary part, so that's why I'm taking I as well. Okay, so now if we substitute this, we get A e alpha x cos beta x plus B e to the power of alpha x sin beta x. Here e to the power of alpha x is common, so A cos beta x plus b sin beta x. So this is the solution corresponding to the roots and alpha minus I beta of, yes. So here the complete solution would be y is equal to e to the power of alpha x times a cos beta x plus b sin beta x plus c 3 e m2x and so on up to cn e to the power of m n minus 1 x. Okay, so that is the general solution for complex roots. Now here remember, this b is not an imaginary number, even though it may look like it is, but it would resolve into a real number. Let's say c1 is 4 plus 7i and c2 is 4 minus 3i, let's say. So c1 plus c2 would be 4 plus 4 8 plus 4i, whereas c1 minus c2i is equal to, so 4 plus 7i minus 4 plus 3i times I. So 4 and 4 get cancelled. 7i plus 3i is 10i times I, which is 10i square, which is minus 10. Okay, so b is not imaginary. Okay, now here if you noticed, we have been working on f of m equal to 0. Now here, how do we get this f of m? F of m equal to 0 is obtained by replacing d by m in f of d, and this is called a auxiliary equation. So f of m equal to 0 is called auxiliary equation. For example, let's say we have d cube y by dx cube minus 13 dy by dx plus 12y equal to 0. Now using the d notation, we will have d cube y minus 13 dy plus 12y equal to 0, or 13d plus 12y equal to 0. Now here we just replace d by m. So here the auxiliary equation of this equation would be m cube minus 13m plus 12 equal to 0. So we take out d, and for 12 also, for the constant also, we get rid of y. Okay, so that is linear differential equation of order n being solved for the three cases of only real and distinct roots, for repeating roots, and for complex roots. I think that's enough for today. Bye for now.